Hi, I'm Lucas. For my A-level computer science coursework, I built a real-time n-body simulation using Python and Pygame. The project was graded and I received an A, and today I'm going to walk you through what it is, how it works, and what I learned along the way. This is the actual simulation running and how gravitational forces will be calculated, and you'll see some of the code behind it as well. So, what is the project? It's a gravity simulation based on Newtonian physics. It models multiple bodies interacting with each other through gravitational force. I built the physics engine from scratch, including my own vector classes and force calculation logic, and there are no external engines involved. So, at the core, the simulation uses Newton's law of gravitation to calculate the force between each pair of bodies. This is then converted into acceleration, which updates the body's velocity and position. To do this, I use leapfrog integration, which is symplectic and allows better stability. It is a smoother and more realistic motion compared to simpler methods like Euler integration. So as we'll see here, leapfrog, we've got two conditions. One's the initial condition and one is the main condition. So we have one that will be the start of the simulation, since it's only called once for each body, and then the next is for the rest of the simulation's time frame. All of the vector math is on its own class, so everything's running from my raw code. So it's all validated, and we've got addition, subtraction, multiplication, magnitude, and a string conversion. That's the only vector operations I really needed. The UI is built with Pygame, and it renders each body and tracks their movement. So everything's using Pygame objects. I've got classes to make buttons in Pygame, I've got text boxes, and then on the simulation screen itself, it draws all the lines, it does all of the text and displaying the bodies on the screen, which if I run the code, you'll quickly see I'm not the best at UI design. I was quite short on time, but we have a screen to add a body, and you'll have all the properties that you can adjust. And then here we have a random body generator, so you can input a random amount of bodies, the mass of these bodies, they'll all be the same color, but they'll generate with random positions and velocities within a certain area that's defined within the code, which I would have made adjustable, but you've got a time constraint with an NEA. So quickly, if we go to the simulation screen, I allow the user to adjust the gravitational constant if they wanted to mess around with that, and the time step. The time step is just how many seconds are in between each iteration. So a shorter time step is like a shorter average between. So when between each time step, if I set it to 10 seconds, you'd have time step 1, that'd be 0 seconds, time step 2 would be 10 seconds. Sorry. In between that, there's you're calculating the average movement over that 10-second time frame, and you're assuming that the force is completely constant and the acceleration is completely constant between those 10 seconds, which isn't fully accurate. And the lower you make the time step, the more accurate your simulation will be, but the more demanding it will also be and the slower it will run. So if we just start the simulation, you can see it's got a scale. I've got a position of the camera, I've got a meter per pixel scale, the time step currently in use, the amount of iterations completed, and the time simulated, which is just iterations times the time step. This scale is dynamic, so zoom in and out. It will change, so does the meters per pixel. If I use the arrow keys to change, the camera's position also changes. The camera's position is a linear function also, so the more you press it, it's increased by the same multiplier. So as you see, the more I press it, the faster it increases. If I go the other way, it decreases quite slowly. It's the same with the zoom function. The more you zoom out, the faster it zooms out. The more you zoom in, the more it zooms in. I went for this scale because the scale of space objects generally is very large, and if you get to even Earth scale, where it's 10 to the 24, 23 in kilograms of mass, then you have to be zooming out a bit. But if you have a very large object, the simulation will automatically adjust the settings so you can see that object and quite a lot of the space around it. The main challenge with the simulation was to run 100 bodies smoothly, which required quite a lot of optimizations, and the main optimization used was utilizing Newton's third law to avoid extra calculations. This quite literally slashed it in half of how many calculations were needed, and required a funky piece of code which I'm not quite proud of. Well, I am actually quite proud of it, to be fair, but as you can see, this for loop iterates through a dictionary which contains each body, and then another loop iterates through it again and calculates the forces and the motion of the body. And we can see that the loop count is initially decremented, and this loop count is initially incremented, and that means that in this J loop, everything, if it's equal to it, so if I loop and J loop are the same, then that's the same body and the force shouldn't be calculated. If the J loop is less than the I loop, then the force has already been calculated because the J loop iterates first, so it'll be 1, and then this will be 0, and then it goes 1, 2, 3, 4, 5, 6 to how many bodies, and then it goes back to I loop and 2. So then we know J loop 1, that's already been calculated, J loop 2 has already been calculated, and J loop 3 and I loop 2, that hasn't been calculated. So then it calculates that force, and it does that until the entire dictionary has been calculated for. And this piece of code is the main time constraint, and this is what causes the n squared time complexity within the simulation. So I mentioned before, this is fully CPU based in Python, and it's no external engines, it's all my code. The only import I use is Pygame and math, and I use math with the square root function within the magnitude. So I wanted the extra challenge of my own vectors class because I thought it'd be a bit cheaty to use NumPy, even though NumPy is a lot quicker and uses, I believe it's C# or C++ for its operations. So this is a very high time step simulation of 100 bodies. You can see that quite a lot of the bodies end up slingshotting, and that's because I don't have a softening parameter within the gravitational force calculation code, and it's also due to the really high time step. So if we zoom in on one of these collisions, you will see, hopefully if they collide, these two look kind of close. There we go. You can see when it's in detail, everything's quite nice and smooth. If you lower the time step, it gets more accurate. You see these two slingshot, that's because they got too close together. Here you go. Closer they get, it's a square root of the distance, so the further they get, the weaker the force. There's another slingshot. It does ruin the accuracy a lot in these massive simulations, but I was constrained with time and I had other I don't know what the word is. I had other things I had to concentrate on alongside my NEA. So, but in a defined system, so if you made the solar system, for example, then as long as you've got the distances to their averages, everything will run very well. It won't break down. I ran it for 2 nights overnight. I ended up getting to, I think, 10 million iterations, and everything ran very well. It didn't break down. The distances stayed the same. There's another slingshot. But yeah, I think overall what I learned from this was UI design is difficult. That's something I've got to get better at. Gravity simulation is ridiculously complex. My research section on my coursework documentation was probably half of it alone, and I should have planned the code much better. I just went into it, started writing code, and the amount of times I had to go back to a class and add something in because I'd forgotten it was ridiculous. But as a developer, it really deepened my understanding of applying mathematical and physical concepts to a computer simulation. Overall, thank you for listening. The code's all released on GitHub, which is linked below, and more projects will be shared through my socials, so stick around if you want to see more of my learning experiences. Thank you.